All right, let's see. Should be going. There we go. All right, cool. So the logistics updates for the morning is like we keep pushing assignments back a little bit. Usually nobody complains when you have extra time to do stuff. So yeah, so we have extra time. Quiz is due, I think it was Tuesday. So like at least there's time either today or Monday to do it, or if you're a weekend worker, weekend warrior worker, then you do have at least a weekend to get through it. And then project number 2, which is what we're going to work on today, like launch that up, start playing around with some Python, see what we can break, and then hopefully fix it. But first step is break it. Then we can learn some stuff as we start to fix it. Yeah, so that'll be due Wednesday. So we'll have like today and then Monday to kind of, today we'll, again, like kind of get in there, see what project 2 is about, and then on Monday, hopefully like get to some specific applications or maybe like targeted questions that you might be dealing with there. Sound like a plan? And so what I did was I went straight into NanoHub. So if you're on like our main, or we can get there from, let's go into Husky CT. Because usually that's where it's like the default starting location of like, I know I need to do something for this class. Let me go into Husky CT, get into 2120. There's my announcement. Module 2, project 2. And then the link for project 2 is the web page. So just like some information about what 4-bar linkages are. There's even like a Happy Valentine's linkage if you want to see like, I think the animation works now. Let's see. No, I thought I fixed it. I don't know why, for some reason, when I push all this onto GitHub, it cannot find that ffmpeg function. Like it's there. Like I've installed it so many times in the little like container that runs this stuff, but it just keeps disappearing. Anyway, so anywhere we see this Jupyter Hub link, that'll bring us over into like NanoHub to like get back into Python and start doing some work. Now we've got project 2. And I'm going to start at the top and run through each code. If you run them out of order, then there might be stuff that's like missing, like variables or functions along the way. So shift enter, keep going down. And let's see, I wanted dx to be 0.95, at least the way that it's listed here. So I've got a system with 3 moving bars that are L1, 2, and 3, and then supports that are dx and dy, like distance away from each other. So if you wanted to like plug in the homework values, we had 0.25, 1, and 1, and then dx was 1. I think in both cases, then you could look at like either 0 or -1/2 to change it up. Well, I'll leave it the way it is. And now, like in the homework problem that we were looking at, we were saying like, all right, angle 1 is in, or everything's kind of like in this fixed state. It is moving, but I just want to figure out like a snapshot, like how fast is everything moving when it's like that. With a computer, we can set up the equations and just say like, all right, I want to know how fast everything's moving from 0 to 360. I mean, we can go further, but it's probably just going to be the same result. Sometimes it's different. Like there are cases where it like flops one way and then like flips over to the other way. Depends on what your system is. So I'm going to say that there are 0 to 360 angle 1 values. So I'm going to change angle 1 to go 0 to 360. Angle 2 and angle 3, so that's A2, A3. They're set as 0 because I'm just going to go through and replace them all. That's what this next for loop is. Oh, len is short for length.
Oh, okay.
Yeah.
So it's the same length as array.
Exactly, yeah. Yeah, so it's nice because then if I want to change this to like 1,000, it's going to be the same number. Or if I wanted to look at it like every degree, like 0, 1, 2, 3, I could say 361 values. And now I have like every degree of angle 1. By default, if you don't give it a value, it gives you 50, and if you give it a value, then it gives you that many 0 to 360 split up into however many you told it to split up. Either it's going to give you the same, like I can't really tell the difference between, if it scrolls down, 50, like on these two smooth curves, I can't tell the difference between 50 and 360 values. So if you have like, this helps if there's like sharp transitions and you want to see more of what's happening, we can increase the number of evaluations. And so what I did was like all that work that we did with like trig and like how do I find theta 1 and the sine theta 1, the cosine theta 1, sine theta 2, all of that was done in one line, and we just did it 361 times. It took 97 milliseconds. This is pretty powerful, right? Like we spent like an hour and a half doing sines and cosines. So you can really ramp up. I didn't change anything about what the process was. Like it's still the same thing of like I needed to define the constraints and say what it was. But once I did all that work, the math, the next step of like just doing trig and math, that one, computers are great for that. It's your best friend. Like what is, like as a philosophy, what is fsolve? Or yeah. Yeah. So let's say a quick way to, if you're like looking, especially when you have like code laid out like this, and you're like, what the heck is this thing doing? You can do like fsolve question mark, and now it gives you a lot of information, but the main thing is like everything about this function that so all of these things are written by like dozens of programmers. It kind of, some people get paid to develop it, some people it's like volunteer time, but anyway. So this function, it's called a root finding function because it's just looking for when it's equal to 0. And so as long as we can, and you can always like rearrange an equation to equal 0. So if we're trying to say like sine theta equals cosine theta, we could subtract one from the other and say sine theta minus cosine theta. It's easier for a computer to find a 0 than it is to find like an exact value. Because with a 0, there's always a sign change. And that one's nice.
What is an NP.0 function do?
The zeros?
Yeah. Right after the A1.
Yeah. Here, this is my hack for looking at documentation. Is I like look at the inputs and then scroll down to the examples. So like NP zeros of 5s gives me 5 zeros. NP zeros of 2, 1 is going to give me 2 rows and 1 column of zeros. So it just fills up an array full of zeros. That process in general is called like initializing your array. We don't have to worry about it. Depends on how deep you want to get into the project. But. So now I have from angle 0 all the way to 360. So I always put it in radians, but I like angles personally. I think there is a np.rad2 deg. Yeah. And all I'm doing is multiply by 180, divide by pi with that. But just so I can see. 0, 360. So angle 2 started at like 70 degrees and then went down, came back up to 80 and then back down. And if I have all the angles, I know where all those links are from this, like RA, BC, and P is a halfway point between A and B, just to see like what's happening to that middle link. And now I can look at like what happened at any point in time. Like what did this thing look like at some point in time? So the red curve is showing me my rocker arm, like what that was doing. The blue curve is showing what the crank arm was moving around in a circle doing. Then that green is the midpoint between A and B, where it's like, yeah, following that one around. And since I did 360, if I say 45, I'm looking at a 45 degree angle 1. And if I look at 110, it's like 110 degrees is over there. Not impressed. All right, so now we can figure out like how fast, since we know where everything is and we know how fast angle 1 is moving, I can plug that in, same set of equations that we had solved in the homework, but again, we can set it up as just like a general solution. And now for every angle of angle 1, I can see how fast theta 2 and theta 3 are moving one way or the other. And here it makes sense, like theta 1 is always going in one direction, like it's always a crank moving counterclockwise. But meanwhile, theta 2 and theta 3 are like positive, then negative, then positive. So they move one way, stop, move the other way, stop. Yeah. And that's like the rocket preview of project 2. Just kind of big picture what's happening. Like So all the equations are kind of like plugged in there. We already went through how to use them, so now it's just setting up some Python so we can like automate the process for us. Oh, up here?
Yeah, it's like way more point on the other side.
Oh, yeah, those inputs. That has to do, like, in, mine says in 13,
Oh, okay.
but if I run it again, it'll be like in 14 or in 20 or something. Like, what is all this doing? Or,
Yeah.
all right, so let's back up a little bit. So in this part where it's like RA, RB, RC, and RP, I'm setting up arrays that are X and Y locations for hinge A as a function of time. So if I look at RA, I'm going to do the transpose of it. I made the rows columns and the columns rows, but here at time 0, hinge A had this XY position. And then at time 1, or when the angle was 1 degree, now it had this XY position. And then same thing for B, C, and T, where those are. So all 4 of those are now like 2 by n, however many like angles I wanted to say angle 1 went through. And then I can take like O, A, B, and C and draw lines through them so that all the X locations end up being dots connected by lines, so I can see what the link, what that 4-bar linkage looks like at that point in time. And that's what this X and Y spot is doing. And then for that given point in time, oh, well, this now I'm just like RA0 is all the X positions, RA1 is all the Y positions. So I'm plotting the path of like, this is what happens over time for hinge A, B, C, and then that midpoint E. Yeah, and there's more than one way to do it, but this is a way to like kind of post-process the results so that we know. We don't just end up with like 50 angles and angular velocities. Well, 50 times 3, so 300 numbers, which is kind of hard to just like wrap your head around. Like, did it work? I don't know.
What's the relevance of the scale P dot plot? Is it RA for 0 colon and then RA is 1 colon? What's the significance of that?
The 0 are the like the first row, so it's all the X values, and then the 1 is the second row, so it's all the Y values. Yeah. So this is kind of like so you have like RA is XA and YA, and then So today, what I wanted you to kind of mess around with was plug in some different lengths or position. Like you can change all 5 of these, like this dx, dy, L1, L2, L3. Those are your main kind of design parameters for a 4-bar linkage. And to start, play around with it and see what happens. Like, do you have any ideas of like what happens if link 2 is like 2 meters? If it's twice as long as link 1 and link 3, or sorry, link 2 and link 3. I'm like, you know what would happen there? Can you build a system like that? Can you even connect?
No, because it's like just out of the stage.
Yeah.
So we're only going a certain amount before we physically stop.
Yeah, yeah. So there's going to be some kind of like physical stop. You know, yeah. What would this even look like?
L1, is L1 the one?
Yeah, if L1 is the longest, and I try to make it go in a circle.
It'll go. I guess if you're going clockwise, it's gonna go a certain amount. Then it's gonna get like held back by L2 from going any further. I don't know
Yeah.
at what point. But I guess that's what the program is for. Or I don't know if the program takes into account. That does not look very good now.
You tried it? Yeah.
Well,
Yeah.
we have a rectangular.
Yeah. Okay. I'll probably end up with a similar problem. So if it's pink like this, or pink or red, like I don't know, I'm partly colorblind, but pink-ish, it still did what you asked, but it's saying like, hey, I don't know if this is really what you want. So you can ignore it and just move on, because it did give us a result. And I get something like this. So if it's not smooth, like that's your first clue of like, all right, something's weird. Like this is not working the way that I want it to. But again, I have numbers, so I can just forge ahead. Just keep plugging things in. Keep running. I can calculate RA, RB, RC. Run. And now I get to my path plot of like what happened as this thing was trying. So blue through hell or high water is going to go in a circle, because I said you go in a circle no matter what. Yeah.
What in the world?
This like yellow hinge C is supposed to be in a fixed location based on constraints that I gave it. So that fsolve part, when fsolve says like, okay, solve the solution to keep hinge C in a fixed location, it got as close as it could, but it kept moving it, and kind of moving it to random locations based on like how many evaluations it had and that, like, but it's not good, right? And so something's broken. And there's like math that you can do to figure out like how big L1 can be based on L2 and L3 and that dx, but who needs math when we can just like break things, right? So yeah, and this is what I wanted to show. It's like if you see like jagged curve, like your curves are jagged and your hinge C is moving around, then something's wrong. Like that, something's got to change. And in this case, I think yeah, that one like 60 degrees. But basically we can only maintain this constraint for like 30 degrees or something, because we can only kind of open it up, close it.
Wait, why is everything? What is this?
Yeah. Yep. Yeah, main goal, like end goal is kind of like to come up with some kind of like engineering design based on this.
Piston, cylinder, assembly.
Oh yeah. I mean, it works okay. Actually, you can click like that run button, so it has like yeah.
Well, there you
I know. Like,
I'm gonna
I
get
like
an
the
awful
keyboard.
like the length where these bars is not going to be integrated with front of each other.
I put it in great.
You know what I mean? This is what piston, cylinder, assembly.
Yeah, at some point, I made it kind of add on
You might have brought a
to
couple
make it like
actually
even longer.
Mike might be cooking.
And
Well, you give it impossible numbers, you end up with something like that.
okay.
Hey, look, I got an actual, like, you got a graph. I want to ask you that, how you get a graph? I got noodles for this guy. Output angle just because of the. I actually really like my recognition. I actually like this one looks correct. What was the second one?
Yeah, you can do it for everybody, and then it'll change all the ratio. Yeah, exactly.
I think it's the same as if you put everything in one, right? If you put everything in 7, I put everything in 5. Ours are going to be 6.
Yeah.
The geometry of the graph will be the same.
I don't think it is. Yeah, there shouldn't be, because it should be like
See that?
No. Mine is 40,000.
Wait, this is kind of cool. Interesting kind of disappeared, but aside from that. Wait, no, wait. If, yeah, if VX is
See why
no, wait. If VX and VY are 0, can't all of them be the same length?
No, because the top one, page 3 needs to be the same.
Yeah.
Actually, no, it doesn't.
I just put everything at 17 and it did not.
Okay, if I put them all at the same length,
Well, that's what I did. Yeah, like if you look at it.
a load of this guy.
Put them all at 17.
50, 500,000 radius. I don't think it's safe. I don't think it's safe. Robo Okay, so wait, I'm going to put a note in here. That's actually important. That's relevant. L1 cannot exceed. No, px and py because like that's actually L1 cannot exceed px. No, both because like my Pythagorean theorem that will be longer to make over the short. I think if you have py squared, L1 cannot exceed.
Hinge B and do like this bad.
What if py is
They have made it worse.
wait, what if py is negative 0.25?
Okay, that makes sense.
Well, like you can't physically do something like that. Like upper end,
Wait, why is Hinge never labeled on my graph?
That's the fixed point.
Was that
That's your fixed point.
this game you play?
That's better. That's better.
That one won't break the bank. I can do that.
And there's no
They're like private classes. You did the right. Yeah, this is what we're playing all over it. Like this on your computer. It won't break the bank, won't break the computer. Oh, I just got this death effect too. Like this.
Well, they don't just play the party.
No, like this guy. He just falls apart, man. Yeah. It's like it's similar to lethal. There's always like this was the only thing I've downloaded is a couple of boring.
So I guess the question becomes, if I multiply everything by 10, does it work? It should. I'm kind of confused with what direction I should take it. I was just like reassigning those variables and kind of running with that.
All right, broke some stuff. Tried to fix it. Nice. So main goal of like finishing, like getting to a finished product of the project is picking some kind of application. So it can be like something in here, like you could say, hey, I want to design a windshield wiper. Skip that. See, I know I'm using YouTube to watch YouTube, but like here, our parts are kind of like O, A, B, and C. If we're
Wait, so we don't have like a full windshield wiper, we just have it right in.
yeah, because we're not trying to solve for like multiple. Because really, what this one is like hinge O is here, A, B, and then here's C, like another fixed location. So A, B, C. And then the rest of the windshield wiper is another 4-bar linkage attached to our first
So
one.
the attached to the motor is point O?
Yeah, because that one's like our main crank arm, the one moving around in a circle.
L1? L2 is that like small vertical one?
Yeah, so let's grab.
Oh, I see. I missed it. I thought it was I just need to mention.
weird linkage where or something, but like one of the points
Well, it just messes like when I fix my values and multiply all of them by the same constant, they all work the same. Yeah.
Trying to copy, paste. Why won't it let me paste it?
Command Shift 4.
There we go.
Got it.
Oh, too many. Anyway. I don't know why I chose green. Yeah, so
But all
like
you have to do is be able to assign linkage, right?
yeah.
So you
And
can kind of eyeball them.
yeah, and like if you were trying to like get this one in particular, like this is kind of a small version of a windshield wiper. So maybe like O to A is a centimeter, and this one's like 4 centimeters.
Yeah, if you assume the length of one, you just kind of like eyeball them.
Yeah. Yep.
So for dy dx, it is upside down, but it doesn't really matter. You can use
Yeah.
so dx and dy are comparing points O and C.
you probably might want to use Photoshop because the actual camera is
Yeah. So this would be like dy, and there's dx. If we're trying to like recreate this YouTube video of a windshield wiper system. Yeah.
I want to make a windshield wiper.
so you're taking a picture or a video on the screen.
Dude, I want to do that. It's going in my favorite job.
Or this was something that I did when I was an undergrad.
Which part turns or which part doesn't? Oh, oil rig. Oil rig is cool. Oh.
Like your knee is your ACL and your PCL, anterior posterior cruciate ligaments, make up a 4-bar linkage that define what your femur, what the bottom of your femur looks like. So the path, when we were looking at, okay, I broke this one. So, like when we were looking at this path of the green path of that midpoint, like point P, that would be the shape of the bottom of your femur, based on how long your ACL and your PCL and where they're connected to femur and tibia. No, tibia. Is that right? Tibia. All right. Yeah. So I thought that was a cool project when I was undergrad. Similar kind of 4-bar linkage design. Oh, the oil rig?
It's in the same video. It was in like halfway through the ACL video.
Yeah, like right here. Similar kind of process. Oh wait, we want spectacle.
I love control volume analysis. Control volume analysis love me. This one's a little conceptually actually. It's not.
Yeah.
You could literally just you could take that other TNT and just rotate it.
So if we're trying to say like, hey, I want to build an oil drilling rig, then we've got like from O to A to B, B to C, and then down here, this would be my DX. This one's my DY. And oil drilling rigs, these things are big, right? So like a 1 meter, that would kind of make sense to say like O to link 1 is 1 meter, like 3 feet, or maybe even like 5 feet long or something, depending on how big the rig is. Yeah. Watt linkage? Yeah. What's watt linkage for? Do you know what that? For suspension systems? Like watt linkage is another 4-bar linkage system. This one is very much, it's not supposed to do, like link 1 is not supposed to do 360 degrees, because there's very few occasions where you would need suspension in a car where the car needs to do a full 360 degree flip. Yeah. Yeah, so here, if I try to stretch that left one up even further, it's going to max out the system. So now something has to break. Like hinge C is broken or something, right?
So if we wanted to replicate that, what we could do is we could take A1, the empty out line space, and change the parameters.
Yeah, exactly.
Or you could just put the values without changing line space and let the graph break.
No, don't let the graph break. Just change the restrictions on A1, right? So it goes from like negative 45 degrees to 45 degrees. Because that's what kind of looks like.
So this one's kind of a cool design because you can pick O and C so that it's your wheelbase. Or sorry, not wheelbase, but like your axle. So how big the axle on your car is? Probably about 6 feet, 6-ish feet. This distance. So like your DX value is how far apart your wheels are. So whether you're considering like a truck or a little kind of Usually four-wheelers don't use watt linkage, but you could say like, hey, I want to make a golf cart suspension, so now like 4 feet or something. And now point P is your main design parameter. Like I want to make sure it's always traveling in a straight line. I don't want it to curve while O and C are while the theta 1 and theta 3 go through as big of an angle as I can get it.
So would you mind explaining what is point P? Is it like your midpoint? You're not like putting values in, right?
That one we calculate as part of the
That's the one that gets tracked in the path.
yeah, so that path that we track that always changes like the shape of it, that's point P. So it's the midpoint of A and B.
Okay.
Yeah.
Are we working on this on Monday?
On Monday we'll like hopefully have some direction. Everybody will have a different project, or maybe everybody's like the same, but either way we'll have specific questions of like, how do I fix this? How do I change theta 1 to only go from like 0 to pi or something?
So can we use the code that you already made, or should we like?
Yeah, definitely. Yeah, take what works. Yeah, don't start from scratch.
Yeah. I was thinking just like edit, going through edit. For like
Yeah.
watt linkage, right? You want to like just edit constraints in your length.
Yep.
And just make sure the graph.
Yeah. So everything is open source, so it's very much like take whatever you want. It's yours. Like now, as soon as you opened it, you own it. You can do whatever you want with it. If you want to keep track, there's always the base version on the website, so you can always go back and start from scratch. So edit whatever you want. You can break it, and we can always get it back to where it used to be. Yeah. Cool. Are we out of time? Yeah, we are. But all right, have a great weekend. Thanks for playing, and we'll be back.